I just upgraded my new cross-section tool so it can estimate the relative signal-to-noise ratio of your images. I've been talking with Mark from Deep Sky Detail about one of his favorite topics, signal-to-noise ratios, and why they matter so much for narrowband imaging. Because at the end of the day, the filter that gives you the better SNR gets you better results with less integration time. Here's the problem. Your camera doesn't label photons as signal or noise. It just records total light. So we're going to get a little creative to figure out what is signal and what is noise. With a few reasonable assumptions, we can estimate the relative SNR between two images using this cross-section approach, and quantify what different filters do on your gear and your sky with your processing. If you saw the last video, you know the process. We load up two registered images and pull a cross-section from the same region in each one. Now, if that cross-section includes a patch of empty sky where there's no nebula and no stars, we can treat that as a background. In a narrowband image, that background is mostly light pollution, sky glow, and other stuff we're just going to treat as noise. And if we assume there's essentially no real target signal in that patch, that background level becomes a direct measurement of how much unwanted light the filter is letting through. So then we subtract that background out. What's left is our best estimate of the signal. And a quick reminder, filters don't magically increase the target signal, they just reduce the noise. That's what this subtraction is trying to isolate. Once we have an estimate of signal and an estimate of background or noise for each image, we can compare them and compute a relative SNR. Once you can estimate SNR, you can stop eyeballing and start answering the real question: which filter gets you the same results with less time or money? If SNR is new to you, don't worry. I'll keep this practical. By the end, you'll be able to compare two filters and estimate which one is best for your situation. When we look at the raw signal in the cross-section, we see that there is an offset between the two filters. In the images, we've just shifted the black point to render the pixels, so the images may look very similar. As we've stretched the image and assigned black point, it's like we subtracted out the noise. This is one part of what's challenging about looking at images to understand how the filters are different. To understand SNR, we need to understand that offset between the two filters. The SNR is the ratio of the signal S, divided by the square root of the sum of the variance in the signal and the variance in the noise. To calculate the signal and noise parameters, we're going to use our cross-sections. For the signal, we can just look at the background subtracted cross-section and use the intensity as the signal. The emission of photons from cosmic objects is random and follows a Poisson distribution, so in the next sub-image, that signal intensity may be different. Ideally, we would want to measure multiple subframes and take the average of the pixel to get an average signal value. But this takes a lot of time and data, especially to compare filters. So we're going to assume that the intensity of nearby pixels is about the same and take an average across a window of pixels to calculate an average signal. This assumes that the sampled region is uniform, the same nebula intensity, and that the measurement of pixels are uncorrelated. However, the process of image calibration, registration, and stacking may introduce some correlations, so using individual subs may be better than stacked images for comparisons. The next term we need is the variance in the signal. For a Poisson distribution, like our cosmic signal, the variance of the signal is proportional to the magnitude of the signal S. And because we calculated S as an average, the variance is S divided by the number of pixels in our window. Assuming we're not dominated by camera read noise, the noise we are measuring is from the random variations of light pollution, which are known to have shot noise characteristics described by a Poisson distribution, where the variance of the background is equivalent to the mean of the background. So for each sub-image, the background magnitude would fluctuate by the variance of the noise. It is this fluctuation in the background intensity, the variance, that is the noise in our images that degrades the signal-to-noise ratio. And here's the big take-home. The more the background strength is reduced, the more the background variance is reduced, and the better the SNR. In exchange for this video, where I'm providing all of this knowledge, visualizations, and tools, and hopefully some entertainment for you, Can you do me a solid favor and just click the subscribe button? That's all I ask. This would really help me out so I can build more content like this. Thanks. Now we have enough data to compare the two filters and get a signal-to-noise ratio for our 6nm and 12nm filters. If we take our SNR equation and plug in the values that we've extracted for each of the filters, we see that the SNR for the 6nm filter is 0.079, and for the 12nm filter, it's 0.066. If we look at the SNR ratio, where we put the SNR for the 6nm filter over the 12nm filter and plug in the values, we get a ratio of 1.2. This tells us that the narrower filter has a factor of 1.2 times better signal-to-noise ratio. If the SNR ratio is 1, then there's no major advantage of one filter over the other. However, even small differences in this SNR ratio can add up quickly. SNR scales as the square root of the total integration time. We can say that the SNR ratio is equal to the square root of the ratio of the total integration times of the filters. If we square both sides and solve, then we see that the 12nm filter needs 1.44 times the integration time to match the 6nm full-width half-max stacked SNR. If you had 10 hours of data with the 6nm filter, you would need 14 hours of data with the 12nm filter to generate an image with the same SNR. That can be a non-trivial amount of time savings, especially if you don't get a lot of clear nights. So what started all of this for me is that I have two H-alpha filters, one at 12nm and one at 6nm, and I wanted to really understand what was I getting as a difference between these two bandwidths that come at different costs. So the primary telescope that I used here was a Edge HD 9.25 inch or 235mm Schmidt-Cassegrain telescope, using the 0.7x reducer, which gave me a focal ratio of about 7. I also have the HyperStar attachment that lets me shoot at a focal ratio of f2.2. These two telescopes really kind of test the different bounds for the dichroic interference filters and how they're going to behave. So let's take a look at the big picture results. If we were to compare our f7 results with the 6nm and 12nm filters to look at the images like we've been doing in some of the demonstration, there's not that many differences. And when we look at the HyperStar configuration, we have a wider field of view. It seems brighter, but it's again kind of hard to tell the difference. Maybe if you squint hard, the 12nm are slightly lower contrast than the top, but this is where we really need that cross-section analysis tool, is to go in and quantitatively analyze these so we can understand how each sub is contributing to the final image that we're going to generate. As you change the focal ratio of your telescope, one of the things that changes is the angle of incidence of photons on the filter. As you go from f10 down to very small focal ratios, that maximum angle changes from just a few degrees all the way up to about 15. Here we're going to be looking and contrasting telescopes at f7 and f2.2, which provide a factor of 3 difference in incidence angle. The whole reason I'm talking about this is because the transmittance characteristics for dichroic interference filters are a function of that incidence angle. Using this equation, as we go to the incidence angle of about 13 degrees, that results in about a 4nm wavelength shift at these more extreme angles. And when we're looking at a 6nm wide filter, with that much shift, what's going to happen is we're going to go from transmitting, if we were directly illuminating the filter with high transmittance, but out at the edge, we're going to end up attenuating our signal down on the edge of this curve. So we're going to end up cutting signal, which may cause some problems. And we're going to see that across the two configurations of the telescope. So let's get into the software and see what it's telling us. Now that we've gone through all of the equations and demonstrations, let's take a look at how to get you operational in Astro cross-sections. Here I'm looking at my GitHub repository that has all of the code, which you're welcome to run it directly from Python. However, if you don't have Python, you can go to the releases and be able to download the binary executable or source code zip files. I only can compile Windows executables right now, so if you have Mac or Linux, you're going to need to download the source code and run it from Python. So I've downloaded the binary executable, I've started up the program, or you can get to this point by running Python on the Astro cross Python file, and now we're ready to use the software. So I'm going to start by loading image 1. In this case, I'm going to start with the SCT at F7, which is this file, and I'm going to start with the 6 nanometer filter. We open this up. This is a linear image. Auto stretch display is turned on, so it has automatically stretched the linear image that otherwise doesn't look like very much. The next thing we want to do is load image 2. In this case, it's going to be the 12 nanometer filter, and it will open on the right. So it does check for some amount of registration, and in this case there's just a little bit of registration error even though these images were calibrated and registered. I think it has to do with a little bit of stretching in the stars that has resulted in a small pixel shift that you can see down here that's off by 3 in X and 2 in Y. So if we want to take a cross section, you start by left clicking in the region you want to start at and dragging across. In this case, we're looking across the horsehead. A second click will lock it in place, and now we have our cross section from the same location in both images. For the analysis that we're about to do, you do want some background that does not contain anything except conceptually light pollution. So if we think that over here in the Flame Nebula that this bottom cross section is also only background, we could do a section here, but I'm going to stick with using our horsehead for this demonstration. There's a few other things you can do here, especially if you're looking at a star. It can be helpful to turn on log scale so you can see the noise down in the lower levels compared to the stars, which you can't see on a linear scale. And if you also want to compare the statistics of the full image, you can turn on histograms and get the probability distribution plots here showing the count of pixels at a given intensity level, in this case on a log scale. The dashed lines represent the median values, which is a good representation of the most typical value found in your image. So we can see that these do have different medians, and they do have rather different distributions about them. But we're interested in cross sections and doing our difference analysis. So let's get back to the cross section. Let's do that a little wider. Once you've got the cross section you want to analyze, click on the Analyze button. That will bring up a new window. And by default, it looks for the lowest point in the image and will select that as background, and the highest point in the image, and it will select that as the bright region. If you want to change the region, you just use the slider and it will select a different position. Same thing with the background region. You can also adjust the width or how many pixels are used in the averaging. So if we wanted to use a really wide sampling, we could widen that, and you should see this widen. Or we could go down to a 20 sample wide sampling to measure our background. There's kind of a balance between getting good statistics and being able to meet some of the assumptions that we covered earlier, such as saying that the approximate intensity of the nebula doesn't change much, so you probably want to keep that kind of narrow. So there's other data here. So let's take a look now at the background subtracted. So this is where we've taken the average value of the blue and subtracted that out of the data so that it's at 0. And we've taken the average value in this region of the orange line, subtracted that out. So now everything has been background subtracted. We see all the backgrounds are kind of level. And when we compare the signal region over here, we see that they are overlapped. So there can be a question about attenuation due to that band shifting. So I actually do a statistical calculation and ask the question, are these two signal intensities statistically similar? The result of that test here is that in this case they are different for where we've sampled, and they're different by about 10%. If we move that around a little bit, since we were including that spike, as we go over here, we see that they are still statistically they are statistically similar. There is about a 5% attenuation that might be observed, but it is not statistically significant. So if we were to compare these two as the ratio of the mean values, we're displaying that ratio here with the uncertainty in that calculation. You can see that that overlaps 1. So again, this is that illustration that they are statistically similar. If we look down on the bottom here, this is now subtracting the blue from the orange after they've been background subtracted. We see no features here, which tell us that we're looking at just signal. That's not going to be the case when we go to the HyperStar later. So the whole reason we were here initially was to calculate signal to noise ratio. So using all of the equations that you saw previously, this software automatically takes the bright value, the dark value, and calculates that signal to noise ratio for you. So in this case, the 6 nanometer filter showed us an SNR of 0.084. And the 12 nanometer filter gave us an SNR of 0.073, giving us a ratio of 1.15. If we square that SNR ratio and get that exposure factor that we talked about previously, this tells us that to get the same final SNR in an image using the 12 nanometer filter, you would have to expose for 1.3 times longer. And you'll get similar results, but maybe slightly different as you scan around. Kind of just showing you what's going to happen as you go to different intensities. Some other features that we have here is you can right click on the graph. You can copy any of these graphs and paste it into other software like PowerPoint or whatever else you'd be interested in tracking. That works for any of the graphs. Rather than putting in a whole lot of controls for the graphs, you can change the scale by clicking and dragging up and down. If you click near that y-axis, you can change either of the X zoom or the Y zoom. Let's see if I can do this back again. If you totally mess it up like I did, you can reset the axes, and we can just, rather than put a lot of widgets in this that you have to click and open other windows, I've made it so that you can scale the axes by clicking near the X-axis and dragging in to stretch it so we can zoom into the section that we want to see. You can also do that on the Y-axis. It works over here to change that. Now, as we've changed the X-axis, if you want to see what that looks like for everything, you can synchronize the X-axis and it'll apply it to all graphs. If you've really screwed things up and want to go back to what's normal, just set reset, and it will do that for each graph. There are times when you're going to have a really large dynamic range, so you can turn on log scales for all of the plots, or you can do that individually. In addition, there's also a table that shows you all of the mean values, standard deviations, and the coefficient of variation, which is the standard deviation divided by the mean, that gives you a relative measure to say there's like a 13% variance in the mean value for the 6 nanometer background, for example. All right, let's go over and look at our HyperStar and see how that is similar or different from what we saw out of our F7 configuration. So starting with our HyperStar data, let's load up the first image, which was a HyperStar with our 6 nanometer filter and our 12 nanometer filter. Now I'll go through the same process of extracting a cross section. Going to Analyze. Maximize the window so we can see it, and you can now see we're still using that width of 20, slightly different number of pixels, so it looks a little bit bigger here. It's selected a background region and a bright region to sample from. Now when we look at the background subtracted region, we see that it did subtract out to 0 for this background. But now we have a difference between the 6 nanometer and 12 nanometer results. Where previously we had no texture in the background subtracted differences, now we can see that the background subtracted out, but that there was a difference of about 0.0025 that was showing up between our two cross sections. Now when we look at the ratio of the bright region for these two, we can see that the ratio between the two bright regions is about 1.3, and when we go do the statistical test, they are statistically different, providing about a 30% attenuation. the 6 nanometer filter has about 30% less signal than the 12 nanometer filter. So now if we go plug all of this into the equations that we talked about previously with the bright regions and dark regions, account for the noise fluctuations in all of those, and calculate the signal to noise ratio, in this case we see that the 6 nanometer and the 12 nanometer filters have the exact same signal to noise ratios. Our SNR ratio is a value of 1. So we can see that our 6 nanometer filter ended up attenuating just as much signal as it attenuated the noise. So there was no advantage in going to the narrower filter for the fast focal ratio configuration. So this gives us an ability to understand, did a filter modify the signal, and be able to understand its impact in the signal to noise ratio. So in this case, the narrower filter that usually costs more is not going to give you more bang for your buck in fast optics due to band shifting. Thanks for sticking around. So what can we say at the end? Well, we have the Astro cross-section tool is now available for download on GitHub. See the link in the description so you can get a copy for yourself. Using this tool, I was able to show that for my f7 scope, the signal to noise ratio was a value of 1.103. And if you square that ratio, it tells you that you need 1.2 times more integration time required for the 12 nanometer filter to provide the same stacked SNR as a 6 nanometer filter. In this case, what was happening is that the reduction of noise provided better signal to noise ratio that'll get you an overall better quality image. For the f2.2 scope using a HyperStar, when we compared these two filters, the SNR ratio was a value of 1. Squaring that is again a value of 1. This means that the 6 nanometer filter attenuated the signal due to band shift and reduced the background, but the combination did not improve the SNR compared to the 12 nanometer filter. From all of this, we can say that in general, narrower filters will reduce more noise and improve SNR. But on scopes with focal ratios less than about f4, signal attenuation due to band shift may negate the noise reduction effects. I hope you've enjoyed this. I hope you can take advantage of these tools. I've done a lot of work looking at these filters and how to understand what's going on to make better decisions. Check out some of my other videos to learn more and see how I've done some of these other characterizations.